Hi everyone, today we will proceed with the chapter Limits and Continuity, right? And we will talk about the commonly occurring limits. We will be proving most of them today, so yeah, there is a lot of things to cover today, so maybe the passing will be a little bit fast, alright? So before we start, I'm gonna revise something from the previous classes, which is the first one, the special trigonometric limits. Right, so I'm pretty sure that you know how powerful this is. Yep, we have used this in our previous lessons, and I told you that we prove this by drawing a unit circle, compare the area, then we use the sandwich or the squeeze theorem, right, to get this. And if you notice, we actually have another one here, which is always paired with this one. And where do we get this from? It's actually from here, then we use trigonometric identities. Then we get the second special trigonometric limits. Alright? And two of them will be very useful when it comes to the chapter differentiation, when you have to differentiate the trigonometric functions by first principle. Alright? So just remember two of them. It will be very useful when it comes to that chapter. Okay, so of course, if you're interested, you can just screenshot this, or you can go and watch my previous videos to see how we prove two of these limits. Alright, then the next things that I want to revise is the limits of rational functions. So as mentioned in our last class, when you are taking the limits at infinity of a rational function, fx over gx, where both f and g are polynomial function, you actually have a shortcut, isn't it? This is because you always do the same thing whenever you have a rational function. You go and divide top and bottom by the highest power in denominator, isn't it? That is why you have something like a fixed answer. If your degree on top is smaller than that at the degree at the bottom, you know that you will get rid of everything on top. You will make everything on top to be 0. So the answer will be 0. Conversely, if the degree on top is greater than the degree at the bottom, you will have some x left on top. That is why the answer will be infinity, and it is either positive or negative depending on that x that is left over. If the degree on top and the degree at the bottom is equal, then it will be some constant attached to the highest power of x. Alright? So these are the two things which I think is also very commonly used when we are evaluating limits. So we will start with today's topic, and we will start with the easiest of all, which is the trigonometric limits. I'm pretty sure that you have seen this table in your high school or even your secondary school, isn't it? And today we will just go through this very quickly, and I will show you how I remember, or not memorize, I just remember this. And of course, during exam, if you somehow forget and you don't have the calculator, you can always draw the right triangle and prove it yourself. Okay, so for sine, you always remember the one at the bottom is always 2. Okay, 2. Then how about on top? You just write 1, 2, 3. Then you go ahead and square root the numerator. Square root of 1 is still 1. Then this will be square root of 2, square root of 3. So it will be 1 over 2, square root over 2, square root 2 over 2, and square root 3 over 2. Then for cos, you know that the cos and sine are complement angle, isn't it? So it will just be the opposite. It will be square root 3 over 2, square root 2 over 2, 1 over 2, finish. Okay? Then for tangent you remember it is always the combination of 1 and sec 3 and square root 3. And how you construct the table? Just draw a line here. Then go ahead and fill in the blank. 1, square root 3, 1, square root 3, finish. And if you still can't remember, you just remember that for tangent pi over 6, which is tangent 30 degrees, it is always the smallest. For tangent 60 degrees or tangent pi over 3 is always the largest. Okay? So yeah, that's it. This is how I remember. If you have some other methods to remember, just go ahead and use your own way. Okay, then if you learn about trigonometric functions graph, you'll notice that Alright, the graph something look like this. You'll notice that this is actually, the graph will actually repeats itself for every period, isn't it? So actually, if you have a sine of pi over 6 plus 2 pi or 4 pi or 6 pi, as long as it is the multiple of its own period, the answer will actually be the same. Same goes for, it's actually for all the trigonometric functions like that. So as long as you can remember this table, then after that, as long if it is somewhere at the second cycle, third cycle, it will be just the same. Okay, so this is what we can conclude from the trigonometric function graph. Okay, then another thing I want you to notice from the trigonometric function graph is the tangent, the secant, cosecant, and cotangent. Alright, so you have to be very careful when you are dealing with the limit somewhere around pi over 2, negative pi over 2, and following the period 3 pi over 2, negative 3 pi over 2. Why? Because this is when the limits does not exist. Remember from earlier classes, we discussed about the limits from the left and limits from the right are not the same. So let's take this example. Okay, let me erase this one. At pi over 2, the limits from the left is actually positive infinity. Then the limits from the right is actually negative infinity. So you have to be very careful about this, alright? Same goes for secant, alright? Secant also at pi over 2, and the period is now 2 pi. So at pi over 2, the limits from the left is actually positive infinity. The limits from the right is negative infinity. Okay? Then for cosecant, the graph will, the asymptote is actually at x equals to pi. And the period is 2 pi. So at when you approach pi from the left, the limits will be positive infinity. From the right is negative infinity. Then for cotangent, okay, so for cotangent, actually the graph look very similar to that of tangent, okay, just it is now like going downwards if you want to describe it that way. So at cotangent, also at pi, okay, also is at pi. If you approach from the left, it is negative infinity. If you approach from the right, is positive infinity. Okay, so what I want to bring to your attention is, again, like I mentioned, be very careful when you are evaluating limits around those values, because the one-sided limits are not the same from both sides. Okay, so yeah, that's all I want to talk about trigonometric functions. Okay, then next we go to the pair with these trigonometric functions, which is the inverse trigonometric functions. As what you learn in your function chapter, in order to make trigonometric function injective, or to make it one-to-one, so that it will have an inverse function, we need to restrict the domain of x, right? We need to restrict the domain so that the graph will be one-to-one, and you will have a function, which a function for the inverse of it. Okay, so actually nothing much for sine and cos, because when you are taking the limits at infinity of sine and cos, you know that it's going to be undefined, because the graph is only until here. It's only from -1 to 1, and that's it. So I'm not interested to talk about two of these. And if you are asked to find the limits of arc sine and arc cos, oh, by the way, this arc sine is also like this. Yeah, you can write this like this. Arc cos is like this. Okay, so if you are asked to find the limits, usually if nothing happens, you can actually direct substitute in. It's either you can direct substitute in, or it is undefined. It is somewhere in the complex plan. Okay, which I'm not going to talk about in today's lesson. Okay, what I want you to take note is the arctangent, arcsecant, arccosecant, and arccotangent. Okay, so a very commonly limits that you've seen is the limit as x approach infinity of arctangent of x. And from the graph here, you actually notice it is actually infinity. This is because of the range and domain. Remember, you restrict the domain for tangent x to make your inverse tangent. So just now, originally it's like this, so now it becomes like this. Means it is from a vertical asymptote, it's now a horizontal asymptote. Okay, this is why we have this. When x approach infinity, the tangent inverse or the arctangent is infinity. Then what about this? When you take the limit to x to negative infinity of arctangent of x, it will be negative infinity. Alright, so it's about like turning around and the asymptotes. Alright, then for this, it's actually the same. When you approach infinity of arcsecant, is actually either infinity or negative infinity. Okay, the limit when x approach infinity of arcsecant of x is equals to the limit when x approach negative infinity of arcsecant of x. Both of them will give you pi over 2. Okay, it's also from the graph here, you go and turn it around and you restrict because you restrict the domain. Okay, so this is what you got. Then what about this? This will be the same. So the limit when x approach infinity of arccosecant, of arccosecant of x will be the same as the limit when x approach negative infinity of arccosecant of x, which will give you a 0, as you can see from the graph. Last but not least, for arccotangent, if it is to negative infinity, okay, I'm so lazy to write already, it will be pi, it will be approaching pi. If it is approaching positive infinity, then the answer will be 0. Okay, so what I want you to do is actually to make your own table of these special trigonometric limits and fill in all of them. Everything that you think you need. Alright? So that is all for trigonometric and inverse trigonometric functions. We'll move on to the next pair, which is the exponent and logarithmic functions. Alright? And these are the very, very common exponential and logarithmic limits that we'll need in some advanced chapters, such as like infinite series, the sequence and series chapter. You usually use this. Okay, so what I will be doing today in this class is I will be proving some of them, actually most of them, which is 1, 2, 3, and 5. Okay, then 4 and 6, I will talk about 6 in a little while. I will just briefly go through, but I will not go and do the full proof. And for number 4 is actually related to number 6. You will need number 4 when you are proving number 6. Okay, so we'll just go through this very quickly. Okay, so for the first one, you have ln n over n. Okay, the exercise one, we need to prove some of them. Okay, so for the first one, limit as n approach infinity of ln n over n. So remember from earlier, I mentioned about how we evaluate limits. We can use L'Hopital's rule. L'Hopital's rule states that whenever you have a limit of a quotient, you can actually differentiate top, then differentiate bottom, right? So I'm just gonna write the proof here, proof, then I write by L'Hopital's rule. Okay, if you don't know how to differentiate ln n, never mind, I will just tell you it is equals to 1 over n. Okay, so this is a derivative for the natural log ln. Okay, then what about the denominator? You differentiate n, you get a 1. And what happens when you put in your infinity? This will just be 0. 0 over 1 is equals to 0. End of proof. Okay, then the next one is the limit as n approach infinity of the n root of n. Okay, so this is a little bit not so straightforward, because as you can see, if you put in infinity, then what happens? But before that, let me just write this in exponent form so that it's easier to see. Okay, oh sorry, not equals to 1. So if you put in infinity, it will be infinity to the power of 1 over infinity is 0, which is actually an indeterminate form. Okay, remember the 7 indeterminate form, only 2 of them can use L'Hopital's rule. So we need to somehow adjust this such that it can be evaluated. Okay, so whenever you have an exponent flying here, flying there, you need to make the exponent fly down. So I'm gonna let my y be n to the 1 over n. Why? Because I want to bring down the power. So I'm gonna take log on both sides. Any base that you like. And for me, I will just use the easiest one, which I'll take ln on both sides. Okay, ln n. You know that by logarithm rules, whenever you have this 1 over n here, you can actually bring down the power, isn't it? It will just be here, 1 over n. Okay, then now can you take the limit? And can you do the L'Hopital's rule? Yes, you can. Okay, so before we do anything, we just go ahead and take the limit as n approach infinity on both sides. And I'm going to write this like this. And this fellow here look very familiar, isn't it? This is what we just proved in our part 1. This is just 0. Okay, so this is equals to 0 from part 1. So the limit as n approach infinity of ln y equals to 0. But I want n to the 1 over n, which is y. So I need to do one more step. Okay, the limit as n approach infinity. Remember your exponent rule. This will just be y equals to e to the 0. And anything raised to 0 power is equals to 1 by definition. Hence, the limit as n approach infinity of y, what is your y? Is n to the 1 of n, which is the n root of n, is equals to 1. End of proof. Okay, so this is all about proving things, and then after you prove all of them, after you derive all of them, you just use it, just directly use it. It will be very, very useful and very time saving, right? Then moving on to the third one, which is even more straightforward, is even easier. And as you can see from here, x remain fixed as n approach infinity. So I'm just gonna write one more thing here, any x. Okay, so for any x, it will be like this. Okay, then just go ahead and prove this. The limit as x approach infinity of this one, x to the 1 over n, if you plug in infinity, this is just gonna be 0. And by definition, if you have anything raised to the 0 power is equals to 1, except for 0. So the limit as x approach infinity of x to the 1 over n is equals to 1. End of proof. See, we just prove it in like 2 minutes. Then I'm going to skip number 4, because number 4 is like something like common sense, isn't it? If your absolute value of x means it is like a fraction 1 over 2, 1 over 3, then you just go ahead and raise it to n, a very big power, then you get a 0. Eventually it will converge to 0. And it is something to do with your geometric series, isn't it? Okay, so I'm not gonna talk about this. But if your absolute value of x is greater than 1, you know that the limit as n approach infinity of xn is gonna be infinity. Okay, it's gonna be positive or negative infinity depending on your x. Okay, so this is all for number 4. And now we'll do number 5. And if you notice, number 5 is actually, this is actually the definition for exponent, isn't it? But never mind, we are just going to prove it like very quickly. So can you use L'Hopital's or whatever directly? No, right? Because your result, if you put in the infinity, okay, this will just be x over infinity is the 0, then to the infinity, so you have 1 to the infinity. And 1 to the infinity is also indeterminate. So you cannot use, it's also indeterminate that you cannot use L'Hopital's rule. Hence, we can't do this. Then what can we do? Like what we did just now, we need to make this power flies down. So I'm gonna take my y as 1 plus x over n to the n. Okay, and now I can take ln on both sides. Ln 1 plus x over n. I bring down the power, it will be here. Okay, and now can I use L'Hopital's rule? To use L'Hopital's rule, I need I need to make it into a quotient, isn't it? How can I make it into a quotient? Okay, so I can write this as like 1 plus x over n divided by 1 over n, right? Now it is a quotient. And can I use L'Hopital's rule? You see, if you put in infinity, this will be ln 1, which is 0, and this will be 1 over infinity, which is also 0. 0 over 0. You have the passport to use L'Hopital's rule. And now I'm gonna get the proof here. By L'Hopital's rule, the limit as n approach infinity of ln y is going to be, you differentiate this. You differentiate ln and inside you have a function, but this function is in terms of n, yeah? Be very careful. It will be 1 over, now your x is actually a constant, 1 plus x over n. Okay? Then you differentiate the inside function, which is negative x over n squared. Okay? Then you differentiate bottom, it will be negative 1 over n squared. Be very careful because you are now differentiating with respect to n. Okay? And this n squared and this n squared can cancel, this negative and this negative cancel. So at the end of the day, okay, let me write it over here. The limit as n approach infinity of ln y is going to be, oh sorry, I forgot the limit here. Okay, then it will be just x over 1 plus x over n, right? Okay, I forgot the limits again. Okay, let me just, okay, limit n approach infinity. Okay, so if we put in infinity, this will just be over infinity, which is a 0. And now what? Okay, the limit as n approach infinity of ln y will just be x over 1 plus 0, which is x over 1. And do we still need to write this limit when n to infinity? No, because we don't have any more n. So I'm just going to write like this. Okay, and by your exponent rule, you know that I need the y. So I write like this, e to the x. And are we done? Yes, because y is just this whole thing, isn't it? So the limit as n approach infinity of what is our y? 1 plus x over n to the n is going to be ex. End of proof. Alright? So actually this is a little bit of like circular logic because this is how we define an exponent. But anyway, if you insist and you want to prove it, then this is how you prove it. Okay. Then we'll move on to the last one, which is, you see, a factorial. Can we use, L'Hopital's rule? If you put in infinity, x to the infinity is going to be infinity. And infinity factorial is of course going to be infinity. Yeah, you can actually use factorial, provided that you know how to differentiate factorial. But we don't know. So what can we do? Actually, the actual proof of these limits is actually you need to use some sandwich theorem, which I'm going to talk about a little bit, but I will not do the full proof here because it is very long. Okay, so you know that by sandwich theorem, you need to have something which is strictly larger than that and strictly smaller than that. You can compare, right? So now we have x to the x to the n over n factorial. What is strictly larger than that is you go and take the absolute value of x raised to n power over n factorial. This definitely strictly larger than this, isn't it? And now, what is strictly smaller? Just go ahead and put a negative. Okay, so this is just like I provide some direction. If you are interested, you can go ahead and prove it yourself. Okay, and now I need to show that this is approach 0, right? I need to show that this is approaching 0. So I'm going to So I'm going to evaluate this, and actually I only need to evaluate this so that I can directly say that this is equals to the negative version of it. And because you are given the limits already, we know that we need to show that this is also approaching 0. Okay, and actually this is when you need to use your just now the theorem number 4, which is this one. This way where you need to use this one. X to the n is equals to 0 whenever your absolute value of x is smaller than 1. So for this, what we do is we need to choose a number n which is greater than the absolute value of x. Okay, so that so that, remember, the absolute value of x over m is smaller than 1. Okay, why I don't put two of them together in a modulus is because you know that modulus of x, absolute value of x is always positive. M is greater than that positive number, means your m is always positive. Okay, then by just now the theorem number 4, you can show that this is actually approaching 0. Okay, so now another thing we need to do with our m is we need to restrict our m such that your n from just now is greater than m. Why? Okay, I will show you in the next. Oh, sorry, let me have a blank patch. Okay, so this absolute value x n over n factorial, if you open it up, it will actually be, okay, you don't touch the top, just leave it like this, and you have n factorial, which is 1 times 2 times until an n, right? And where should we put our m? You see, our m is smaller. Okay, maybe I should use red color. Our m is smaller than n. So means if I put it into a n factorial, it should be something in the middle, isn't it? It should be somewhere here, m. Then after that we have n plus 1. Then after that we have n plus 2 until n. Okay? So from here to here, from m to n is actually n minus m factors, isn't it? Okay, so because previously, oh sorry, it's actually until here, yeah. So because previously you have m factors. Then from here to here you have n factors. So from here to here you have n minus n factor. And this is very nice. Why? Because you can say this is smaller or equals to the absolute value of x to the n over n factorial n times n minus n. Okay, then you just go ahead and simplify this one using the exponent rule to the m factorial, then times what? Okay, m to the n, m to the n. Okay, right? This is supposed to be a capital M, yeah? Oh, yeah, okay. Then maybe one more step. You just group all of them together. Then absolute value of x, n over n. Okay, absolute value of x over n to the n. Which is, this fella here is what we have here, isn't it? Yeah, this one. Okay, so I write a note for you in case you are stuck here when you are trying to prove this. This m to the m over m factorial does not change when your n increase. It's actually a constant. Okay, because you are choosing an m, you choose your own m, so it doesn't matter. It will always be there. Okay, it will not change when whatever n you take. Okay, so hence from here, using just now theorem number 4, we can show that this as well as n over n factorial is actually smaller than 0, and it is greater or equals to 0. Okay, by just now number 4. Hence, the limit it's actually another layer of sandwich theorem, if you notice, of this one, n factorial is equal to 0. Then you come back to here, this is 0, right? This is now already 0. Let me just erase the whole thing. 0. Then what is the negative version of 0? Is also 0. Sandwich theorem, you stuck your x to the n over n factorial in between 2 0, means this is also 0. So end of proof. But this is not a legit proof. I'm just going to show you the idea of proving this. Okay? Yeah, so that is all for the common exponential and logarithmic limits. Okay? We'll proceed with the last pair, which is the hyperbolic and inverse hyperbolic. So for hyperbolic and inverse hyperbolic, it's actually more to like definition, and actually if you remember the graph, you can also find it from the graph. Okay, so I'm going to directly go to the exercise, which we use the definition of the hyperbolic function to find the limits. Okay, so actually we cover most of them in this exercise. So 1a, limit as x approach infinity of sine x. Okay, so if you remember the definition for sine, it is, okay, limit as x approach infinity, x e to the x, okay, e to the x minus e to the negative x, which is 1 over e to the x over 2. Okay, let's check. Are we correct? Yep. Okay, so be very careful with the negative and positive, yeah. Okay, because for sine is negative, for cosh is positive. Okay, then what you're gonna do is, actually you can directly see the answer, but I'm just gonna write one more step. X approach infinity of x e to the x over 2 minus 1 over 2 ex. Okay, so if you take x to the infinity, this will be 1 over infinity, so it's gonna be 0. Then this is still a infinity over 2, hence the answer will be infinity. Check the graph, see whether it makes sense or not. When x goes to infinity, yeah, it should be going to infinity as well. So, yep, that's it. Then what about negative infinity? So like I said in previous classes, I think when we talk about infinite limits, I told you that do not confuse yourself. What I always do is I bring the negative over and I give it to my x, right? Then I just go ahead and use the definition. X approach infinity, e to the, now it is negative x. Okay, then minus 1 over e to the negative x, which is actually opposite of just now what we did, right? So it is now 1 over e to the x minus e to the x over 2. Okay, so if you like, you can go ahead and separate this. Okay, just do one more step. X approach infinity, 2ex minus e to the x over 2. So now as you can see, this is 0, this is infinity, but you have a negative sign in front, hence it will be negative infinity. Okay, check the graph. When you are going to negative infinity, yep, you have a negative infinity. Makes sense. Okay, next is cosh. Okay, so cosh is actually very similar to sine, just like it is now plus instead of minus. Okay, so the limit as x approach infinity, e to the x plus 1 over e to the x over 2. And you know lah, because it is plus, so it doesn't matter. This is your 0, this is your infinity over 2, it is positive infinity, finish. Okay, then for this, actually doesn't matter because your, okay, negative x plus 1 over e to negative x over 2. Okay, if you flip it, okay, it will still be the same because plus e to the x, because it is a plus, it doesn't matter who comes first. So this will be 0, this is infinity, hence it is positive infinity, finish. Check the graph, positive infinity, very nice. Then next we go to hyperbolic tangent. Hyperbolic tangent, you know that it is sine over cos. So how you remember it is like this, because sine is minus, isn't it? X approach infinity of, so it is minus on top for the definition. Okay, e to the x plus 1 over e to the x. But you can't directly put in infinity. Actually you can, but it is not nice because you have a infinity over infinity, which will result in L'Hopital's rule. So what I do, I divide both top and bottom by 1 over e to the x. Okay, and you see what happened. X to the infinity of 1 minus 1 over e to the 2x, which I don't have to worry, isn't it? Because I'm taking to infinity. E to the 2x. And it doesn't matter if I put the x, e to the x together at like some in this position, because I know that this is going to be 0, right? If I put in infinity, hence it will be 1 over 1, which is the positive one, finish. Okay, then for hyperbolic tangent, okay, I think there is a typo here. It shouldn't be a y equals a. Okay, so as I said, you just go to what's that? Change your x to be tangent hyperbolic negative x, sorry, negative x. So just do the exact same step. E to the negative x minus 1 over e to the negative x over e to the negative x plus 1 over e to the negative x. Okay. Then you going to can write like one more step for you. 1 over e to the x minus e to the x over 1 over e to the x plus e to the x. And because I want to make it like easier to compute, I'm just going to do it like this. I put the e to the x at bottom, it doesn't matter. And you know that this is going to be, okay, let me just clear some space here. Alright, so I'm writing over here, yeah. Okay, so right here, the limit x approach infinity of this will just be 1 over e to the 2x minus, right? Now you have minus 1 over 1 over e to the 2x plus 1. Okay, this is 0, this is 0, hence it is negative 1 over 1, which is negative 1, finish. Then you check the graph. Okay, just now when it is approaching positive infinity, yeah, it is 1. If it is negative, then it is negative 1. Okay, very nice. Then we'll move on to the next one, which is secant hyperbolic and cosecant hyperbolic. And I already give you a hint here, which is we use the identity. Your secant hyperbolic is the reciprocal of cosh. Okay, so just now cosh, when we approach infinity, is what? Cosh is infinity. So it's just going to be 1 over infinity, which is 0. Okay, then for approach from negative infinity, it doesn't matter, isn't it? Because for both of them are actually positive infinity. Okay, so it is again 1 over infinity, hence it is 0. Check the graph for secant hyperbolic. Okay, secant hyperbolic, you see, when x approach infinity is approaching 0. Negative infinity also 0. Hence, two of them are correct. Okay, next, cosecant hyperbolic. Okay, this is when you need to be a little bit careful because your your sign is one is positive, one is negative infinity. Okay, so if it is like x approach infinity, it is 1 over infinity, so it's 0, no problem. Then what about this? It's 1 over negative infinity, isn't it? Okay, 1 over negative infinity is actually also 0. It's actually also 0. It is also 0. So if you look at the graph, it's actually like this. And if you go to positive infinity, it's 0. Go to negative infinity, also 0. Just that, okay, I don't think this in the exercise, but if you look at this, when x is at 0, the limits from the left and limits from the right are not the same, isn't it? So the limit when x from the right of cosecant hyperbolic, it is equals to positive infinity. Okay, then for this one, the limit as x approach 0 from the left of cosecant hyperbolic is equals to negative infinity. Okay, just take note on that. Okay, then last but not least, oh yeah, so this is what I'm talking about, the cotangent hyperbolic from one side. Okay, but before we do anything, okay, so for cotangent hyperbolic, the graph is here. Okay, let me erase this one. The graph is here. If it is going to positive infinity, okay, the limit when x approach infinity of cotangent hyperbolic, it is going to be 1. From the graph, you can see, right? Then the limit when it approach negative infinity of cotangent hyperbolic is going to be a negative 1. Okay, the horizontal asymptote, sharing the same horizontal asymptote as tangent hyperbolic. Okay, then what about this one-sided? Okay, so whenever you see one-sided limits, you immediately comes to your mind is the h approach, isn't it? We throw away our x, use the c plus h or c minus h. But in this case, it is not necessary because your x is also approaching 0. So you have no choice but to actually you can see from the graph, but if you insist want to do the algebraically, which I don't think it really works, it really helps. Okay, so what's that? The definition for that, it is because for tangent hyperbolic, it is minus on top, plus at the bottom. Then cotangent hyperbolic is the inverse of it. It is the reciprocal of it. So it will just be plus on top, minus at the bottom. Okay, so this is a little bit different because you are taking 0 instead of x approach 0 instead of x approach infinity. So what you will do this time is you multiply top by e to the x. Okay, e to the x. Then now you have, I hope you know where I'm going. This will just be a 1, right? Then e to the 2x minus 1. Okay, the reason why I'm doing this is because okay, it actually doesn't matter because e raised to the 0 is still 1, still divide by 0. So you have to do your positive negative analysis. Okay, so whenever you approach 0 from the right, means you are raising to a positive power, and you know that whenever your x is positive, okay, whenever your x is greater than 0, 2x is greater than 0, e raised to the positive power is greater than 1. Hence, this will be positive. And on top, it is plus, of course, it is positive. Positive over positive, you know that this is an infinity, and you know that this is a positive infinity, finish. Okay? Then for this time you are approaching from the left. Actually, it's the direct same, it's actually the exact same approach. E to the x minus 1 over e to the x. Then you multiply top and bottom by e to the x. E to the x. Then now you have limit x approach 0 from the left. E to the 2x plus 1. E to the 2x minus 1. Okay, now whenever you have your x is approaching from the left, means it is negative 0.00001, smaller than 0. You raise e to the negative power. E to the negative power is smaller than 1. It is 1 over 2, 1 over something, 1 over something, isn't it? So this will be negative. This will be positive. Positive over negative, it is a negative infinity, finish. Then you check your graph. Okay, from the right, it is positive infinity. Yup. From the left, it is negative infinity. Yup. Very nice. Okay, so that is all for hyperbolic function. We'll move on to the last part of today's chapter, which is the inverse hyperbolic function, which I'm not going to do in detail. I'm just going to show you the graph, and yeah. So for sine hyperbolic, because if you really want to go ahead and find the limits, you actually have to refer to the definition, and you need to take the limit from the definition, which is very complex because as you can see, you have a ln here, and somehow for tangent, actually you are somehow get an imaginary number I. Okay, so just going to show you the graph. Okay, so for sine inverse, if it is going to infinity, it is infinity. If it is going to negative infinity, it's negative infinity. Then for cosh, you need to be a little bit careful because to negative infinity, it is actually undefined. Okay, but for positive infinity, yes, it is positive infinity. Then for tangent, as I told you just now, it will be involving I, because as you can see, the graph will just like within this region only. It will not exit. So if you take the limit to infinity, actually, you will not have any solution on real number plane. Okay, then this cosecant, secant, and cotangent hyperbolic. Okay, so if you're interested, you can just go ahead and try all of these. Okay, so this is all for today's lesson, which we derive all the commonly occurring limits in those transcendental functions. So in the next lesson, we'll be doing question evaluating limits again using those formulas that we derive in today's lesson. Okay, so the next lesson will be the last class that we will be evaluating limits. Then after that, we will do the epsilon delta definition proof, and we are done with the chapter. Alright, so that's all for today. See you guys in the next class.